I know what you're thinking right now. Another video about survey prisms. Aren't you beating a dead horse by this point? Well, maybe, but maybe not. I still see people doing high precision work with 360s all the time, quoting millimeter accuracy. That tells me there still isn't industry-wide acceptance of the importance of those little glass reflective devices that we use for almost any measurement for our total stations. When trying to sort out my thoughts for this video, I sat down and contemplated why this topic isn't more mainstream in the survey industry. Why are we so hung up on the angular spec of the total station as being the main defining characteristic of accuracy of the points we measure? Is it lack of awareness of how much target error affects the accuracy of our measurements? Perhaps it's the perceived notion that the total station is almost solely responsible for hitting those elusive zeros on our check shots. Maybe it's the fact we can buy a $30 prism from China that's actually not that bad. In fact, I just put out a video that demonstrated that very point. Or is saying a 1-second instrument is good and a 5-second instrument is bad just an easy way to specify point accuracy? But is this really the case? What if I told you Surveyor A can get better results from a 5-second total station than Surveyor B using their 1-second total station in the vast majority of situations just by altering their prism choice? Today we're going to do an in-depth exploration of the impact prism choice has on point accuracy. We're going to talk about something I call the triangle of target error, and we're going to see how ball prisms or spherically mounted reflectors fit into those equations. We're going to look at theoretical testing using air propagation, and we're going to get suited and booted and head into the field for some real-world testing, because anyone can talk the talk. I want to find out if these ball prisms can actually walk the walk. Let's get after it. Alright, what are these things? It looks like someone honed out a ball bearing and stuck a corner cube reflector in it. Well, that's actually not too far off from reality. The round body or shell of these prisms lends itself to machining practices that allow for extremely high precision manufacturing. Oftentimes, the body can be ground to tolerances of less than 1/100th of a millimeter. And because they are nearly perfectly spherical, they are very typically used in what is called a nest, which essentially is a concave surface that precisely matches the body of the SMR on one side, and the other side can mount to a variety of flat surfaces by either a magnet, machine threads, adhesive, or screws. The high precision manufacture of the body combined with the careful centering of the corner cube prism inside it allows these prisms to obtain levels of centering error that typically just aren't possible from traditional survey prisms. If you've seen an SMR before, there's a good chance it was being used with a laser tracker. Today we are going to focus on SMRs purpose-built for the surveying industry, and more specifically, the construction or engineering/layout survey industry. Quite often these are called ball prisms, and some retain the SMR moniker for the retro reflectors that were purpose-built for laser trackers. Although they are fundamentally similar, SMRs designed specifically for those laser trackers can cost well over $1,500 per prism. These purpose-built SMRs significantly reduce the prism centering error compared to the ball prisms we'll discuss, dropping the error from about 1/3 of a millimeter to 1/100th of a millimeter or less. Are we going to see a big difference going from 1/3 to 1/100th of a millimeter when using a total station? Probably not one that's worth a few $1,000s per prism. As such, today's video is focused on the variant made specifically for a total station. SMR, ball prism, your choice on what to call it. When put to use in the surveying industry, they are most commonly adopted to set highly accurate and convenient control points that will be used either to resect off of or for monitoring. You can use them in place of any other prism as well, but they really excel when used in conjunction with these two uses. Because of the plethora of ways you can mount them, but also because they are extremely accurate. And for most monitoring projects, accuracy is the name of the game. They can be mounted on pretty much any flat surface and can be easily rotated to point in any direction on the side of the wall they are fixed to. There are layout tools that can be used with them as well that expand their versatility. In my construction surveying days, we would be living and breathing high quality resections. A setup in backsite often isn't ideal. You are typically under a time crunch with tradesmen waiting on you, and you need to set up in a very specific spot with limited sightlines to be able to lay out exactly what is being asked of you. Sure, you can start to traverse into that perfect spot, but if you don't close out and post-process that data, those open traverse legs that took you there also just added a bunch of error. Now that most of my total station work involves traversing, I primarily use SMRs as a very accurate and quick to set common or bracing points, as they are sometimes called. When you adjust your traverse using least squares, it's common practice to triangulate each traverse leg. This is done by observing a common point from both ends. When we post-process the traverse leg, it is adjusted knowing that each measured point is supposed to share the same coordinate value. Because this point doesn't need to be occupied, only observed, it's a fantastic candidate for an SMR. What I usually do is find some metal in a spot that triangulates my leg fairly well, then either use my pencil or better yet, my automatic center punch to make a dimple, set the magnetic nest over that dimple, and pop the SMR on and point it at my total station. After I shoot it in from one end of the leg, as I'm walking past it on my way to move setups, I'll turn the SMR to aim at the point I'm on my way to occupy. I do a ton of traverses that involve going up and down stairwells with very short backsights. These SMRs are extremely helpful in those situations. This style of demarcating a common point is also handy because it leaves a very indiscrete permanent control point. We surveyors know how common it is for our control on the ground to get destroyed no matter how much we flag them up, but it's hard for a D8 to accidentally take out a steel pillar on a building, electrical utility vault, or fire hydrant. I can keep two of these in my vests with the magnetic nests attached, and I forget about them until I need them, at which point they're very easy to access. The star of today's video is the Delta SMR Kit. A few months back, I came across a fellow Canadian surveyor by the name of Lucas Jackson. He was using a ball prism or SMR, which wasn't entirely new to me, but what caught my eye was the very tricked out kit that he was showcasing alongside of the SMR he was using. We started chatting a bit back in March, and it turns out he teamed up with JEOC to create and distribute an SMR kit designed by surveyors for surveyors. You may remember JEOC if you've seen some of my earlier videos. They created some of the prisms in my Prism Showdown video and make the mini tripods I've talked about in quite a few of my previous videos. To say I was impressed with the kit Lucas was offering would be an understatement, and a few weeks ago, I finally got my hands on my very own Delta SMR kit. It came with 5 SMRs, 5 concrete anchor nests, 5 magnetic adapters, 5 magnetic nests, and 15 nylon nests, 5 screw and glue nests, along with a mini pole adapter and a 5/8 threaded adapter to use on any tri-brack or conventional survey pole. It also came with a stack of dual-use stickers that work great in conjunction with the magnetic nest. Alright, there's a lot going on here, so let's break this down piece by piece. First up, the SMRs themselves. These were designed to have the very common prism constant of -16.9 millimeters for Trimble or TopCon total stations and positive 17.5 millimeters for Leica total stations. The same as almost every mini prism out there. They have a 1.5 inch or 38 millimeter diameter, which works out to use a height of target of 1 inch or 25.4 millimeters when used with any of the magnetic or nylon nests that they come with. You get 5 of them in the kit and they seem extremely sturdy and well made. Now, I'm not going to shoot them with an arrow or throw them across my yard like I did the prisms I tested in my last video, but if I dropped one of these on the ground at chest height, I think they would hold up just fine. The actual prism is protected by a metal lip. They are also quoted at having a centering error of both the prism and the nest they use of under 0.5 millimeter. Keep in mind, a good traditional survey prism quotes a centering error of about 4 times that at 2 millimeters, and you're paying a pretty penny for a 360 that gets you 2 millimeters of prism centering error. Next up, the magnetic nests. Before we dive into these, I just have to say the build quality and packaging on this kit, top to bottom, is through the roof. They didn't cheap out anywhere, and man, do I love this case. It's small, easy to carry, it's solid as a rock, and everything has its place. It will really bring out the inner OCD in anyone. Back to the mag nests. Pretty self-explanatory. They have a very strong magnet that holds the nest to any ferrous, flat surface, and another magnet that holds the SMR into the nest. Delta gives you a handful of these dual-use stickers with a kit, which you can refill from them. They give you a professional-looking way to demarcate your control points, so when you're done for the day, you can pop the magnetic nest off and your sticker is left behind so that you can precisely center the magnetic nest next time you need to use that control point. You can also use a center punch to make a dimple, which you line up with the center hole in the mag nest, or use a pencil or paint pen to trace the exterior of the mag nest as another way to demarcate the control point. You have plenty of options. And of course, since the SMR is round and the nest is concave, you have 180 degrees by 180 degrees of freedom of where you would like to point the prism. But we don't always have steel or other ferrous surfaces we can work with. How about wood or plastic? That's exactly what the magnetic adapters are for. Drive one of the supplied leg screws through the center of one of those, and you have now solved that problem. When you're done with that control point for the day, you can either take the SMR and mag nest with you and leave the adapter behind, or when you're done with the project, back out the lag bolt and take the adapter too. Okay, well that's all well and great, but this is construction. We have metal sometimes, sure we often have wood or plastic surfaces, but the vast majority of what we're surrounded by is concrete. What do you have that will work there? Well, you have 3 options. You can use concrete leg screws and the magnetic adapters we just looked at. You can use drop-in anchors for the 3/8 concrete anchor nest that come with the kit, neither of which is hard to use at all. Use a hammer drill and the appropriate masonry bit for whichever nest you wish to use. I like the drop-in anchor option because they're 50 cents a piece and the anchor nest comes with you at the end of the day. When you come back, you thread the nest back into the anchor you left embedded in the concrete. One thing that could be an issue with these is if you have a client that doesn't want you to screw something into concrete. Now, most clients get that we surveyors need to leave permanent or semi-permanent control points behind so we can come back, and it's pretty hard to do that without defacing the site in some way. Whether it be drilling or setting a concrete nail, scribing a cut cross, or using either of the aforementioned methods for the SMR kit. However, sometimes on sensitive sites, those will still be an issue. That's where the nylon nests come into play. Hop onto Amazon and pick up a battery-powered hot glue gun that will work with your tool battery of choice, most of which come with a bunch of glue sticks to get you going. This one uses Milwaukee batteries, cost me $30, and takes about 2 to 3 minutes to get to temp. Then give the backside of the nylon nest a good dab and place it wherever you want. I couldn't believe how well these hold, and with a Chinese hot glue gun and a stick of glue that costs about 10 cents each. They're not popping off by themselves, and when you're all done with that project, grab your hammer and chisel and you can chip it off and use it on the next site. Delta also sells replacements of all these nests. They also just started to make these screw and glue nests. Like the nylon nests, you can use a hot glue gun or you can secure it in with screws. Concrete screws in concrete, wood screws in wood, metal screws in metal, as long as it's not heavy gauge steel, of course, but if it was, that's why you have the mag nests. There's a nest for pretty much any kind of flat surface you're going to encounter on a construction site. And even if you don't have a nice flat concrete surface, you can set those concrete anchors in shotcrete or masonry. And when you'd rather use a tripod and tribrac on an existing control point, you have the adapter. Need to do some layout or pickup with a mini prism? You got the adapter for that too, that works with the aluminum 1/4 inch threaded poles from a Leica GMP 111. It even comes with a punch in the set. I prefer my automatic center punch that lives in my vest, but it's nice it's there just in case I forget it one day. It's a hell of a kit for what Lucas currently sells them for, around $1,200 US. If you only got the prisms, that works out to about $240 a prism. Where can you get a prism with sub-millimeter centering error for $240? But then you get all of the extra accessories and the case with it. That's a deal in my books, and I shouldn't have to say it because I've said it 100 times, but I'm going to just in case. I did not get paid for this video, nor any video I have ever made. I'm giving a shout out to this kit because it's a good deal. And if you do construction surveying, I can't see how this wouldn't improve your accuracy and efficiency. The next question we need to address is, why would we need a ball prism? Most round prisms have prism centering error of 2 millimeters. Is 2 millimeters really not good enough? Sure, if that was the only error source, 2 millimeters sounds great. But the prism centering error is far from the sole source of error in a total station measurement. Hell, it's not even the only error source that's physically located at the point we are measuring. We still have to account for all the sources of error at the total station and the sources of error between the total station and the target. We're talking about the horizontal and vertical total station centering error, the pointing and reading error, the trunnion axis error, the level compensator error, error from the ATR's determination of the center of the prism, error from the EDM measuring the distance to the prism, error from measuring the atmospheric conditions, error from varying atmospheric conditions, and so on. Now, I don't want to spend the next 10 minutes talking about all the error sources of a total station measurement, but I do want to get into the 3 main sources of error that live at the point we are measuring. We can lump those 3 error sources into a group called target error, those being pole plumbness error, prism centering error, and target centering error. I like to think of these 3 error sources that make up target error as the 3 sides of a triangle, the target error triangle. If we want high accuracy total station measurements, we have to identify and minimize every error source. And a ton of error can live around the target we are measuring. Once you start running through the error propagation, it can be quite shocking what kind of impact target error can have. This is one reason it annoys me to no end when I see client specs requiring 1 second or half-second instruments with zero mention of the other 10 plus sources of error that affect the point being measured. It's such a flimsy way of trying to specify deliverable accuracy. We have error propagation. There are better ways that have been accepted by the industry. But I digress, a topic for another video. Back to the error at the target. Let's break down each side of that error triangle. When we scribe a cross in concrete, hammer a 10-inch spike in soil, or set a concrete nail, we are demarcating a point we want to define with coordinates. Those coordinates we give that point are intended to apply to the intersection of that scribe, the center of the spike, or the dimple of the concrete nail. But not all points we demarcate are created equal. How certain can we be that we are placing the tip of the survey pole or centering our tribrac plummet on the exact center of that scribe, spike, or nail every single time? If I set that control point on Monday and come back to it on Thursday, is the tip of my pole in the exact same spot? Well, it's definitely not in the exact same spot, but what kind of deviation are we talking about? Maybe when I measured it the first time, I was 1 millimeter to the east of the center, and when I come back to use it a few days later, I'm 2 millimeters to the west. Now you might be saying, 2 millimeters off? Not a chance. Do me a favor right now. Pull your wallet out, take out 2 credit cards, and look at how wide they are. That's 2 millimeters. Now, if you're using a freshly calibrated tribrac or mini tripod, I'll agree, you probably won't be off center 2 millimeters. 1 millimeter, though, is absolutely possible. And if you're using a concrete nail with a dimple, I would give you sub-millimeter centering with a pull tip there as well. But with any full-size rod without a force centering control point, 2 millimeters or more is absolutely possible depending on what kind of physical mark demarcates the control point. I like to refer to this source of error as target centering error. We make measurements to the center of prisms, not the demarcated control point. Our prisms are elevated above the control point on top of a prism pole or tribrac or mini tripod. And since we cannot elevate the prism perfectly above the control point, we introduce another source of error. One I refer to as pole plumbness error, which does apply to tribracs as well. This is the random error introduced from the imperfect leveling of either a tribrac, if that's what your prism is sitting on, or the prism pole, if that's your tool of choice. This is not to be confused with a miscalibrated level bubble. That is a systematic error that we are going to assume doesn't exist because the pole bubble has been calibrated correctly and recently. In reality, those are probably two pretty big assumptions. This is a random error source that is directly correlated to the sensitivity of the bubble of either our prism pole or tribrac and the height the prism is elevated above the control point. Let's look at a carbon fiber topple pole and run through some example numbers. These poles are usually outfitted with a 40-minute level bubble. This means that the level bubble vial, and thus the pole or tribrac it's attached to, is out of level by 40 minutes when the bubble in the vial has moved 2 millimeters, or the bubble is touching the side of the black ring printed on the top of the fisheye bubble vial. If we assume the average surveyor can visually discern when that level bubble has moved just half a millimeter off center, or half the width of a credit card, and we have a pole height of 2 meters, that means we can be fairly sure that the prism sitting on our pole is plus or minus 6 millimeters or better, centered above the tip of the prism. If we swap out the carbon fiber rod with a Leica GLS-12 or tripod and tribrac that have a height of target of around 1.5 meters, and most of those use 8-minute level bubbles, that plus or minus 6 millimeters drops to 0.9 millimeters. And if we swap that out with a mini tripod, the pole plumbness error essentially becomes inconsequential. Of course, these numbers assume the poles aren't bent, the level bubbles are calibrated, and if you're using a tribrac, the plummet is calibrated as well. When you drop height of target, all of those possible sources of systematic error have much less of an impact. Basically, we want highly sensitive level bubbles and/or short target heights. As we can see from these examples, the last thing in the world we want to do when we're chasing accuracy is to use a 2-meter topple rod with a 40-minute bubble, especially when paired with a 360-degree prism. Which leads me to the third error source at the target, prism centering error. This one is pretty straightforward, and it's typically defined by the manufacturer of the prism. It more or less refers to how well the optical center of the prism aligns with the mechanical center or the axis it pivots on. In other words, the Leica GMP 101 has a 1 millimeter prism centering error. This means we should expect the exact center of the glass in the prism to be within 1 millimeters horizontally and vertically of the center of the top of the prism pole when the defined height of prism is applied. I've done 2 videos that talk at length about this error source, but to give you a very quick overview of what to expect, a very good nodal mini or circular prism has a quoted 1 millimeter prism centering error. 2 millimeters is considered good, and the creme de la creme from Leica, the GPH1P, has a 0.3 millimeter centering error, but that puppy costs $1,600 per prism. More often than not, you're probably around a 2mm centering error on most round prisms. And on the topic of nodal versus non-nodal prisms, just stay away from non-nodal prisms. They might be cheaper, but that's really not a good place to save a few bucks. You're better off with a cheap Chinese knockoff nodal prism than you are a branded non-nodal prism. Now with 360s, you have to pay a lot to stay at that 2mm mark for prism centering error. In reality, you're probably going to be higher than that. Now I can sit here all day and tell you don't use a topo pole, don't use a 360, use a mini tripod, use an SMR, but until I start providing some evidence, it's essentially conjecture, just me flapping my gums. This is where error propagation comes in. By using the accuracy specs that the manufacturer has provided us of our equipment, and for error sources that cannot be specified by the manufacturer, we can either estimate, calculate, or use a combination of the two to derive expected point coordinate accuracy. We will use the pre-analysis tool in StarNet. If you're not familiar with it, I have a dedicated video on the subject, but it essentially estimates the standard deviations of surveyed points using industry-accepted error propagation equations, potential observations, and instrument and setup accuracy specifications. I wanted to see what kind of difference in potential accuracy we could expect doing a 3-point resection with a topo pole and 360 prism, a Leica GLS12 and GPR111, both of those on scribes, and then see what we can get using SMRs. We'll use a centering error of our total station of 0mm because we're doing a resection, and as such, we aren't trying to center over a known point. We'll use a 1-second total station that has an EDM spec of 1mm plus 2 ppm. To calculate the potential target error for each setup, we'll need to do a bit of manual error propagation because StarNet lumps the 3 sides of the target error triangle into one value that they simply denote as target centering error. I certainly wouldn't mind if they split it up like I did in the error propagation program I wrote, Survey Buddy, but perhaps in a future release of StarNet they can do that. But also, I might be one of the few people that want that level of control. For the prism poles, we'll assume we will have a physical target centering error of 1mm. In other words, we can center the tip of the pole in the scribe plus or minus 1mm. We'll use the manufacturer spec for each prism to obtain the prism centering error. The GPR11 has a 2mm prism centering error. The manufacturer of this 360 doesn't specify the prism centering error, but testing has shown it to be around 4mm. And the manufacturer of the SMR lumps the prism centering error and the target centering error together because they also make the nests at under 0.5 mm. We'll calculate the potential pole plumpness error by multiplying the height of target by the sine of the bubble sensitivity divided by 4. We divide by 4 again because we believe we can level the pole so that the bubble is only off center in the vial by 0.5 mm instead of 2mm that the angular spec refers to. So the pole plumpness error for the GLS12 is 1.5 meters times the sine of 8 minutes divided by 4, which works out to 0.9 millimeters. The pole plumpness error for the topo pole is 2 meters times the sine of 40 minutes divided by 4, which works out to 5.8 millimeters. And the pole plumpness error for the SMR is 0 because the center of the prism defines the control point, not a demarcated point underneath it, aka the height of target is 0. To calculate the total target error for each, we take the square root of the sum of the 3 error sources squared. For the GLS12, that's the square root of 1 squared plus 2 squared plus 0.9 squared for a target error of 2.4 millimeters. For the topo pole, that's the square root of 1 squared plus 4 squared plus 5.8 squared for a total of 7.1 millimeters. And for the SMR, since the manufacturer gave us the combined spec already, we need to use that, which we'll say is 0.5 millimeters. We are now ready for StarNet. I'll create a resection with 3 surrounding control points, all of which are about 50 meters away from the resection point, with coordinate standard deviations of 2 millimeters in each axis. We'll assume we're taking dual face observations to each point. With the topo pole, we get 10.6 millimeters for the semi-major axis of the error ellipse at 95%. In other words, if we repeated this resection 20 times, 19 of those times we should get coordinates created by the resection results within 10.6 millimeters of the true location of the center of the instrument. With the GLS-12, we get a huge drop from 10.6 millimeters to 4.8 millimeters for the semi-major. We lost more than half of the error in our setup just by swapping out poles and prisms. And with the Delta SMR, we drop again to 3.4 millimeters. That's a 30% reduction in total point error compared to already using a very high quality prism and pole. To better illustrate how substantial a difference that is, we will rerun the adjustment, still using the SMRs, but we'll swap out that 1 second total station for a 5 second total station. The resection results went from 3.4 millimeters in the semi-major axis to 3.7 millimeters. This is very important to fully grasp and a great example of why I think clients trying to govern survey accuracy by mandating total station accuracy spec with no thought or concern of the total survey network is an approach devoid of nuance. It's also important to understand that sure, the GLS-12 and GPR-111 got a sub 5 millimeter accuracy at 95%. Isn't that good enough? Again, I go back to the fact that error compounds. If your setup location is good to plus or minus 5 millimeters, then how can you be confident that the points you're laying out from there are also going to be good to 5 millimeters? You can't. That would be ignoring all the error that gets introduced from your foresight. Now I can sit here in my office and do calculations until the cows come home, but there's nothing quite like getting out in the field and doing some real world testing. I set up my total station on an assumed coordinate value, calibrated the level compensator, ATR, and collimation. I set a referenced and stable backsight using a JEOC mini tripod in GMP 101 about 70 meters away with an assumed azimuth and observed 5 SMRs that were surrounding my setup point that were mounted using a variety of methods from concrete anchor nests to magnetic nests and a nylon nest. Simultaneously, I also measured 3 check shots on mini tripods with GMP 101s. I ran 3 rounds, each using both faces. After that, I reset my backsight and measured 5 scribes directly under the SMRs using a GLS-12 and GMP 101 with a 1 millimeter prism centering error. So as of right now, we have 5 control points defined by SMRs. We have 5 adjacent control points defined by a GLS-12 with an HT of 1.5 meters using a bipod and GMP 101, and 4 check shots defined by mini tripods and GMP 101s. We're going to do 2 resections, one using the SMRs and one using the GLS-12 on the scribes, and check out both times to the 4 mini tripods. The deviation between the coordinates defined by each resection and the original setup coordinates will give me an indication of positional error. And the check shots will give me an indication of positional error plus orientation error. First up is the resection using the GLS-12 and the GMP 101. Now keep in mind, the GLS-12, in my opinion, is the best survey pole out there money can buy. It has locking vertical graduations, an 8-minute level bubble, and a carbide tip. And the GMP 101 has a 1 millimeter prism centering error. It's my go-to prism for most of my traverse work. I would not have gotten these same results with a carbon fiber topo pole and a cheaper prism. 0.500 was my resection point, and I saw a horizontal deviation of 1.7 millimeters from my initial setup point and a vertical deviation of 0.4 millimeters. Not too bad, a bit worse than I would expect horizontally. Vertically, I do usually see sub-millimeter accuracy over shorter distances, so that was no surprise. And what about the orientation? Well, that's where things kind of fell apart. And remember, these check shots were on GMP 101s on mini tripods that haven't been touched since I started the day and are on very stable surfaces. The closest check shot was 0.9 at 16 meters away and was out 2.4 millimeters horizontally and 0.3 millimeters vertically. 0.7 at 42 meters away was out 3.7 millimeters horizontally and 0.4 millimeters vertically. 0.8 was 46 meters away and was out 5.9 millimeters horizontally and 0.0 millimeters vertically. And the original back sight at 68 meters away was out 5 millimeters horizontally and 0.0 millimeters vertically. Those horizontal values were not what I expected. I expected to see 2, maybe 3 millimeters, but not 6. We didn't see issues in the vertical because the vertical angles don't really have anything to do with the resection results past the definition of the position of the resection point. The vertical angles reference gravity, not the orientation defined by the observations to the points. Next up was the resection using SMRs. The position of the setup point saw a deviation of 0.4 millimeters horizontally and 0.4 millimeters vertically. Sub-millimeter resection results are a great way to start off. In the same order, 0.9 had a horizontal deviation of 0.2 millimeters and a 0.2 millimeter vertical deviation. 0.7 had 0.3 millimeters horizontally and 0.4 millimeters vertically. 0.8 had 1.2 millimeters horizontally and 0.5 millimeters vertically. And the original back sight that was 68 meters away was 0.4 millimeters horizontally and 0.1 millimeters vertically. I'll be honest here, when I saw these results, I did not think this old total station had this kind of quality left in her. This old girl has probably traveled to more states across the country than the vast majority of Americans and has seen its fair share of action. Even knew it wasn't a high-end instrument, and here we are squeezing sub-millimeter accuracy from it. That's got to tell you something. Target error can have a huge impact on the final error in the coordinates of the points we are defining. And if you can sort out the target error triangle, you can get some pretty impressive results. Now, we are trying to measure random error here, and because random error is just that, random, I couldn't in good conscience do one test and call it a day. So in the name of science, I went back out to that exact same site 2 more times on 2 different days and repeated the exact same test step by step. On the second site visit, the SMR resection was 0.1 millimeters off horizontally from the assumed setup point and 0.0 millimeters off vertically. The check shot to the original back sight from the resection was 0.4 millimeters horizontally and 0.1 millimeters vertically. 0.7 was 0.5 millimeters horizontally and 0.1 millimeters vertically. 8 was 0.9 millimeters horizontally and 0.7 millimeters vertically, and 0.9 was 0.6 millimeters horizontally and 0.1 millimeters vertically. Sub-millimeter results on all our check shots and a tenth of a millimeter on our resection point. Come on, that's pretty damn good for this old total station. Now, I mentioned I was concerned about the results that I got from the GLS 12 last time I was out here. And during filming, I got distracted and was rushing more than I should have and didn't check the level bubble of the rod. Rookie mistake. When I did check the pole level bubble this time, I saw it was out 2 millimeters. I have no one to blame but myself for that, but it does bring up an interesting point. How often are surveyors checking the level bubble of their prism poles? I'm usually fairly strict about it and check it at the start of every new job, or if the pole went through rough travel or was bumped, but the pole plumbness error we calculated previously assumes a level bubble in perfect condition. If that bubble is out of calibration, that's error on top of what we calculated, and hence why we saw 6 millimeters of error in a 46 meter observation. Let's see how this same setup does after fixing the prism pole's level bubble. The resection point was 0.6 millimeters horizontally and 0.0 millimeters vertically, almost 3 times better than our first go. The backside point was 2 millimeters horizontally and 0.0 millimeters vertically. 0.7 was 1 millimeters horizontally and 0.1 millimeters vertically. 8 was 1.4 millimeters horizontally and 2 millimeters vertically, and 9 was 1.8 millimeters horizontally and 0.1 millimeters vertically. Now, these values aligned much more closely to what I would expect to see based on experience in air propagation on this setup. We had an average error of 1.5 millimeters horizontally with the GLS-12 and GMP-101 on the 4 check shots. Pretty damn good. But with the SMRs, we dropped that down to around 0.6 millimeters. Again, maybe you don't need sub-millimeter accuracy, but accuracy and time spent in the field making measurements are intertwined with each other. If you can double your accuracy by using one prism over another, you may be able to take half as many redundant measurements or push your observations twice as far, which means fewer setups and you getting to wrap up your day earlier. Whenever I do these review style videos, I try to remain objective and point out the cons or what I don't like about the product I'm looking at. This one was tough though. The Delta SMR Kit is priced extremely fairly. The build quality is top notch, the accuracy is obviously there, the usefulness is there. I like the company and what they stand for. I don't think I could really say one thing I didn't like about the kit if I'm being honest. If you forced my hand, I guess I would request more ways to mount the SMR or maybe other layout tools. Perhaps an SMR mount that would work on round pillars. Alright, let's get right to it. The $1,200 question. Should you go out and buy one of these SMR kits? It depends. If you're a legal land surveyor that only really pulls out the total station when you need to tie a property corner that happens to be under trees and you can't use your RTK receiver anymore, don't bother. The small reduction in prism centering error versus a traditional prism won't really do much for you when you attach these to a prism pole. Now, if you're a construction surveyor or setting out engineer, as it's called in some parts of the world, get this kit or any SMR kit. It doesn't really matter to me which one you buy, but this is a good kit and it's one I've tested and it's one I can stand behind. Delta really thought this one out and put a nice package together here. I spoke to Lucas and it sounds like he's going to have to adjust the price for these kits in the fall of 2025. So if you're on the fence about getting one or not, I would recommend not waiting too long to make that decision. When showing up to a construction site you work on every day or every week, the first thing you usually do is drive or walk around and set up all your tripods and tribrachs on your control points so you can set up your instrument exactly where it needs to be for your resection. This can take 30, 45, or an hour plus depending on what your site looks like and how many points you want to use, especially considering you can't really carry more than one tripod and tribrach at a time. Conversely, if you have this SMR kit, it weighs a couple of pounds and setting up your control points is as easy as popping a ball prism onto a nest. No stomping in the legs, centering the tribrach, leveling the legs, leveling the thumb screws, measuring the HT, hoping the control point you were setting up over wasn't disturbed since you were here last week, and all that hassle for a less convenient, less accurate way to reference a control point. Now, you'll obviously still need to use a tripod and tribrach sometimes, but if you can, use an SMR nest. It's just a better solution. When we look at the target air triangle, using an SMR strengthens all three sides simultaneously. Prism centering error is better than 99% of the round prisms out there, pole plumbness error is eliminated, and target centering error is in the range of 1/100th of a millimeter. You're just not going to beat SMRs in terms of accuracy if you can use them. If you're surveying pre-construction and you're in an open field, you can't really use them as they were intended to be used. Although even then, you can still use the adapter in this kit and pop an SMR on a tripod and tribrach if that's what you're using. If you take one thing away from this video, let it be that target air triangle. Reduce each and every side as much as possible without hindering your efficiency too much, and you'll be off to a good start. Use mag nails instead of spikes, shorten your height of target, and use more precise level bubbles whenever possible. And stay away from low quality, non-nodal, and 360-degree prisms when accuracy matters. Well, that wraps up another one here at the Third Dimension. Thank you all for watching, and as always, subscribe if you want, like if you feel it's warranted, and I'll see you next time.